Welcome you all. I am here to discuss about a new chapter, new discussion. After the discussion of the stress at a point, stress in an element, stress strain diagram, and then statical indeterminate structure. So every time we have discussed about the stress in element, stress at a point, how to find out the stresses, corresponding strains. We have fought to find out all these unknown values every single time we tried in a different manner. If the boundary condition is there, if the boundary condition is not there, and if the boundary condition is there, then what are the conditions has to be there, and all this corresponding their geometry, their availability, applicability. Likewise, we have discussed various instances regarding the stress and their corresponding values. Now this is also one kind of extension of the same, and I can say this is basically this chapter is named as principal stresses or compound stress, principal stress or compound stress or principal strain also. So although we are not going to discuss much on principal strain, we'll only follow the principal stresses and the corresponding discussion just that will be extended. We'll know first of all, if I know the stresses, we understand what is stress, and I think stress in element, how it is converted to the stress in a point. Basically, if you'll see at the end of this video or end of this lecture, you'll find I have given a link, and it's nicely discussed about how the principal stresses are without any mathematics. You can also calculate, and it's amazing to understand that. Also, you can. I thought it is worthy to discuss all this to share with you, and you people also go through. It was nicely given how the principal stresses or this where from this principal stress concept has come. It will be a little bit more clarified on that. If I know the stress, when again what is the concept of the name has come principal stresses. Why so? So basically, or in generally we say whenever there is a stress is available or stress is going to develop within the body, if the stress is going to develop, so that is not always in a plane or in a particular plane. You know why this principal stresses has come, as I said, why it's a principal. When there is a stress, the stress is always come in a group. We have discussed during the discussion of the normal stress, we have discussed during the shear stress, all we saw the stresses has come in always in a group, not a single, or a single stress is not coming. Although there is a uniaxial stress, corresponding strain will be there, and we imposed all the uniaxial stresses and their corresponding efforts or their responses or effects. Then we accumulate the every individual effects, and we found out the strengths. So that means, in summarize, if I'll summarize the things, there are two major things. One is the stresses which are going to come, they are in a group. If there is in a group of stresses are there, then we will not have a single valued. This is not itself is a single valued function. It's a function of gathering of different kind or different values. Like if any force will come, that force will have two component. One component corresponds to normal, one component corresponds to shear. One will create a normal stress, one will create the shear stress. So the in into altogether, if I'll go stress in element, I get 18, or out of 18 again I get 9. That means there must be some resultant of that. To calculate that, then we need to find out the resultant, and the principal stresses basically talks about that. And whenever there is a stress on a body, they will not a single value, rather it's a compound value of the stresses will come into the picture. If the compound value of the stresses will come into the picture, then how to evaluate? Point number one. Then point number two is that whenever I am applying the load is not always perpendicular to that line or that plane or that particular point I am talking about within the material. It may be perpendicular or it may be inclined. If it is inclined, then how to evaluate? If all these conditions, all what are the kind of condition? And when I am saying about the stresses, then that stresses are always on a flat or perpendicular plane, or if the plane is inclined, then how to evaluate? All these issues or all these considerations are going to be discussed within this principal stress and compound stress, within this topic. Now, slowly we'll go into that. First of all, we'll talk about the stresses on an inclined plane. If it is an uniaxial stress or only a single stress will be there, then how to evaluate the stress which is going to develop in the uniaxial. If there is a uniaxial stress on an inclined plane, then how to evaluate. Here, some of the points has been discussed based on this figure. If you go to the figure, just you can see, you can clearly see that figure. A bar has been taken, which the bar is named as A as well as B, and it is subjected to a externally loaded external loading, and external loading is P. This and it is in equilibrium. Since it is equilibrium, you will have a pair of loading is going to have construction to maintain this corresponding equilibrium of that particular beam element. Now I take a imaginary surface, which is that surface I named as Mn over here, and it is cutting this body into that body has been cut by using this imaginary surface Mn, and it is the imaginary surface I am talking about. It is perpendicular to the x-axis. I believe it is no much clarity is required over here. It's a simple one. Now the normal stress which is acting on this body, because the perpendicular, because we know whenever we want to find out the stresses, stress is nothing but the applied load to the perpendicular plane where I am interested to find out. It is nothing but that sigma x or sigma xx, the first x along the loading line where the load is along that. So load is along the x, and the perpendicular plane we are talking about, the cutting plane we are talking about, which is perpendicular to that. So sigma xx or sigma x can be represented as P by A directly. That means this P is not this is the applied force. Due to that, a resistive force or a reactive force has been developed within the body, and we are equating that force is equivalent to that the amount of resistance also is P. So that P by perpendicular area A, that perpendicular area, the plane which is passing through the perpendicular area A, if the stress is distribution is uniform over the entire, at this moment we are considering all these stresses which is coming out, all these points are average of that. This is the, or it is entire cross sectional area, it is uniform. The load is, although it is looking like at a point, but it is not exactly point. You just see, you may ask that although I am looking into the this cross section as a square, showing as a square, then how it is a point? If I am go on decreasing this size, if I cut this all this from this side, from this side, from this side and this side, if I am going on cutting or going on decreasing the area, at the point I'll get a square, or I can get a triangle, or somebody may say it may be a circle. Yes, it can be obtained all this kind. Since it is easy for us to evaluate or to represent or physical manner, it is easy to define, the mathematics will be easy to for a rectangular cross section to find out the area and all this A into B. If I'll go for a area, then pi by 4 d square or pi r square I have to introduce. All this for a circular area, half into B into H I have to introduce for the triangle. So all this area, the complexity, it will not a simple one. So we assume that the area which is we are talking about a point is a smaller point or the smaller section, that section created as a rectangle or a square, it will be more easy to evaluate, more easy to represent in form of mathematics. Now the free body diagram, if I'll just trying to draw, it's just the average stresses I'm talking about. Whatever the average stresses we see, all these points on this surface are under same amount of the forces, and the projected area we are talking about, this area, the projected area, it's a square or a rectangle, whatever you take here. We are assuming here it's like a the cross sectional area is just a rectangle or resemble as a square. Now, if I know it's for it is not for the inclined plane, rather it's a straight plane. If it just I'll convert into in a different form. Now to obtain this complete picture in an inclined plane instead of a perpendicular plane. Now I am cutting this body by using a cutting plane which is earlier I have taken Mn. Now that cutting plane, the same object with a new cutting plane having a area of PQ which is at an inclination, and that inclination we have not mentioned. Then how to evaluate the same? Earlier the perpendicular plane which we have taken, that perpendicular plane P by A directly we did. Now in this case, then how to find it out? Now you see the average stress which you want to calculate, that will be on a perpendicular plane which is inclined to the earlier case, or it is perpendicular to the force which is acting on this surface, which is not perpendicular. This surface, the cutting surface, the imaginary surface, they are not parallel to each other, or they are not this the PQ, this PQ part or the PQ plane is not perpendicular along the X line. Then how to represent? It is looking like, if I'll make it instead of 2D, if I'll make it 1D, so it's look like the third figure I am showing here. That means the PQ plane over here, and the projected line is an inclined plane or slant line. From the equilibrium of this body, it is well known that the resultant of the stress must be horizontal, which is shown in the dashed line. So now how to calculate, how to evaluate? For let's say that angle we are talking about, the PQ, that is install an angle for the specifying orientation of the inclined section PQ. We install an angle theta between the x-axis. Let's say we are considering the theta instead of the perpendicular plane we are talking about. If I'll take a normal onto that plane, that perpendicular is at an angle of theta to the x-axis. Now how to find out this principal stress or the normal stress or the stress on that body on an inclined plane? To find out the stresses along on this section PQ, refer figure, refer the figure it is showing below. Just like looking like in earlier case, we have, it was a straight, here it was straight, now it is instead of straight line we have an inclined line, and that inclined line, the P which is acting on this point, will have two component, one normal component and one shear component. That now the force which is acting in the first case, which is directly perpendicular to that, and there is no shear form is there. So since there is no shear, so we took it as a, there is nothing is going to happen regarding the shear, only the normal stress is going to create it. This force component, if I'll write this normal component and the shear component, I believe it is clear how from we get this n is equal to p cos theta. I'll take p is equal to, this is the theta angle, it has been taken, so this is the p cos theta, and this q is equal to p sin theta. Now if I got the forces, individual forces, then I can get the individual stresses, the area which is initially we have taken A. So now the A has been converted, because the area is the perpendicular A, perpendicular area if I am taking A. Now the new area which is inclined plane A1, the A1 is relevant to A1 cos theta, because initially it was flat, it was perpendicular, now it has slant, and that slant area is theta, so A by cos theta. I think it is clear from here. Now the standardized sign convention, that means we got, you see, we got a two different reference over here. The normal stress we got, it is sigma by the normal stress which we got here, the normal stress sigma A by n by A1, and tau the shear stress q by A1, and A by N1, that means which we have, again we have discussed here, n is equal to p cos theta and q is equal to q sin theta. Q is equal to p sin theta. Now putting these values over here, n by A1, A1 is A by cos theta, so n by A1, so n by A1, n is equal to p cos theta divided by A by cos theta, so it will be converted to, we will come to that how it will be converted, and I think most of you are now, you got how we are getting these values. And the stresses, the normal stresses, or normally the stresses sigma theta are positive in tension. That means the sigma theta at an angle of theta we are considering as the normal stress, and they will be termed as, no more termed as sigma x, instead they will be termed, because the plane we are calculating, the plane is not perpendicular to x-axis, the plane is at an angle of theta to the x-axis, and the stress is going to develop on that theta angle, theta plane is sigma theta, and the corresponding shear stress also will get tau theta. And both, how we will take positive and which one will take negative, the first part will take the positive one, this one by using the first one, the positive, the like as their normal stresses, and that means the sigma theta, if it is tensile then we will take positive, if the sigma theta is negative, if it is compressive. Similarly the shear stress, if it will make a produce a positive, when they tend to produce a counterclockwise, when they take the anti-clockwise and clockwise based on the the kind of moment they will create, based on their moments they will be termed as sigma theta. And now the sigma theta can be represented as whatever we read in earlier case, then now it has been converted to by sigma theta is equal to, that means the inclined plane, the normal stress on inclined plane, it is equal to, earlier sigma is equal to p by a cos theta. And now if I'll make it the theta is equal to 0, that means when the theta is equal to 0, it will be termed as p by a only. So now you just see whatever we have discussed, this area no more is a by no more is only a, instead of that it is a by cos theta, and this is sigma theta. How you got, I have already discussed. Similarly the shear stress also we get. Then what is the use of discussing all this normal theta, inclined plane, and what is the next part of that? It is not always true that we will have, as we know, in every case it's a three-dimensional case. Again, if it is three-dimensional case, we reduce it to two-dimensional cases, and we will find it out the two-dimensional cases if there is a all these kind of stresses which are coming on the body, then how to evaluate the resultant forces or the resultant the inclined plane, the normal and shear stresses which are involved or which are developed on that. We are trying to discuss about only the corresponding or subsequent forces, or sorry, corresponding or subsequent stresses on a resultant, to count the resultant stresses. Most probably we are talking about the resultant stresses, because of the stresses are coming on a structure or on a point, on an element in a gather manner or in a group, and from that group we are calculating the stresses, basically the again in form of normal and shear individually. Now if they give the normal and shear the principal stresses, principal, sometime also I can define in this form. Sometime also the stresses which are developing on a principal plane is called the principal stresses. Again, then what is principal plane? The plane where the shear stress is equal to 0. It is defined the principal plane, the plane termed as principal plane when shear stress is 0. So you may ask, somebody may thought about what is the principal plane, how you are making it the shear stresses are 0. I think I have already discussed during the discussion, some live classes, during the live classes I have discussed about the how the shear stress come into the picture. If I rotate the angle, or if I am rotating the, or if I am changing the angle instead of the plane, if it is the shear stress is only develops when there is a rotation of the plane with respect to the reference frame. If there is no rotation, or if it is perpendicular, then the shear is not going to develop, and the shear stress component is going to be 0. I'll also discuss, I'll try to discuss if something, some similar kind of stuff will come, I'll discuss here as well. Now here in this particular part, after discussing about the uniaxial normal stresses, or the uniaxial loading on an inclined plane, what are the component, we have now discussed about the shear and normal component. Now the new uniaxial cases, introducing the notation sigma x is equal to p by a, in which sigma x is the normal stress on a cross section. Also using the trigonometric we can write, or we can represent both the normal and shear stresses in a other form for uniaxial condition only. If the load is only uniaxial type, then we will have, instead of having the sigma x by, what is we got, sigma x cos square theta, or p by a cos square theta, and that p by a sigma theta we have discussed, sigma theta p by a or sigma cos square theta, that cos square theta has been again converted into half of cos 2 theta, and all this, that means sin theta and cos theta, it has been termed, one is sin component, one is cos component. Cos component refers to the normal stress, sin component in a oblique plane, the cos component of the stresses will refers to the normal stress, and sin component of that same will refers to the shear stress. Now what are the condition, what is principal stress, we'll talk about more on a 2D cases. Before going to the principal stress, you may ask, you have already, I have already discussed what is principal, why it is principal, because we are trying to find out in a gap from a whole or a pair or a group of stresses, we are trying to find out resultant. Then the principal stresses can be evaluated by two major way. One is analytical method, one what we have just now discussed for unidirectional cases. These are nothing but the analytical steps we have shown. And now if it is more than the normal stresses, or the number will be more unique in, because we know nowhere will get only sigma x, only tau, or combination of only sigma or only sigma and tau. There may be in a complex situation we have in a 3D, but in 2D case at least we will get two normal and one shear. If so, then how to calculate, we are going to discuss about that in this particular section. Now as I said, it is there are two different method, one is analytical method and one is graphical method, and this principal stress or combined stress also talks about that, and this lecture will talk about the analytical part, and one more lecture I'll talk about the principal stresses by utilizing graphical method. Also graphical method is known as Mohr circle, how to plot the Mohr circle if a stressed element or stress at a point, if the number of stresses are there at a point, then how to find out the values of the principal stresses by using the Mohr circle steps. Now, in under these principal stresses, there are four major conditions for 2D cases or 3D cases also. We are talking about only 2D here, and there are four major conditions may arise. One is direct stress condition, that means only uniaxial direct stress condition. One is biaxial or biaxial direct stress condition, or pure shear, or biaxial and shear stress condition. Although I'll go by one, I'll not go one by one. I'll talk about two different cases, that means direct stress as well as biaxial stress condition. And direct stress already I have discussed about that. Still I'll link to another kind of explanation to that. And biaxial normal stress, instead of biaxial normal stress, if we'll go directly to biaxial shear stress and make it the shear stress is 0, then I'll get the biaxial stress condition, and biaxial shear stress condition, out of which if I'll make it the biaxial stress condition as 0, the normal stresses are 0, I'll get the pure shear condition. That means the values can be evaluated, and what are the maximum value, and where is the plane, the principal plane we are talking about. In this step analytically we will find what is principal plane, that means where the shear stress is 0 I am saying. So we have to find out mathematically how we will find the plane where shear stress is 0, and what are the stresses on a principal plane, what is the maximum and minimum, a range will be there, and those are will be called as maximum principal stress and minimum principal stress. How to evaluate, we will discuss here on. Now the first case is direct stress or uniaxial stress condition, which I have already discussed. Now you may see here, although we are always taking a beam kind of structure, or here I am showing a differential element which is having under a stressed condition instead of force. I am having a stressed condition, the sigma x and sigma x, and there is no tau or no shear stress is there. Direct stress is only there. If the direct stress is there on that particular element, I caught a portion of that, or I take a line BE. What is that BE? Now dy is the length, and what is this dy? What is the ds? And the dy is nothing but this length is the, or AB is the dy, and the length of B will be termed as ds, and it is the inclined plane on which I am interested to find out the normal and shear, and sigma n is the normal stress that we termed as sigma theta earlier, and similarly the tau is the tangential stress acting on the that plane B. Now the area, if I want to calculate, I am just this I know, the dy I know, AB I know, and the unit thickness, the thickness of this body, if I'll just try to draw the original form I want to say, that will be looking like in this form. It will be more clear. Let's say if I'll take this one as the unit thickness, when I'm saying it is, I'm talking about, this is the unit thickness I'm talking about, and this unit thickness, under this unit thickness, if I know this unit thickness, then I'll just multiply dy, because I know this was the length I took as a dy part. This was the dy part, from here to here it is dy, and whole length is AB is dy, and if I multiply the unit thickness, then I can get the area. Now the ds is equal to a by cos theta, what we know from our earlier discussion. Sigma theta is p by sigma theta or sigma n, tau theta or tau here whatever it has been shown, all this we can get here in this form, P by A cos square theta or sigma x cos square theta, because it is sigma x has been applied, P by A cos square theta, because if you just see, if I'll make theta is equal to 0, that means if I'm talking about this is theta, if this is theta, then it is 90 minus theta. So accordingly this relation will change. If I'm interested to calculate from this point or this point, just I'll put the change the angle, I can get the values are in a different way. So now this, if I'll make this theta is equal to 0, then this sigma x will be termed as sigma theta will be sigma x. That means it will, because sigma theta is equal to, if theta is equal to 0, so a by cos theta cos 0 1, so I'll get only ds is equal to a. At that time this b and ab will be coincide with each other, they are going to coincide with each other. So based on that uniaxial stress condition what we have just now discussed, it is just an extension of that. You may ask, if I am interested to find out this value, then why I am taking this one as a, because I am talking about the since stress is the internal part of the body. If I'll chord the body inclined on an inclined plane, or inclination, some inclination to the, instead of that, if I'll chord the body here in this direction, that means if I'll chord this body in this direction, then what will be the problem with that? Can I do that? Yes, I can do that. Only for that, when I am doing, only I am perpendicularly, when I am cutting the body, there is another case, only biaxial or direct stress condition will, instead of this, everywhere we will see, slowly we are going to talk about a triangular element every time instead of a rectangular element. That means stress distribution on a triangular element instead of a rectangular element. As I said earlier, if I am taking a point, why I am considering the point as a rectangle or a square, neither a triangle nor a circle, because it is mathematically, it will be easy to evaluate that area. Similarly, if I am interested to calculate the inclination plane or inclined plane, when it is under the all kind of stresses, that means it's a combination of the stresses are there, that means normal stress as well as the shear stress, it is easy, or it will be it is giving better concept or better clarity on this all kind of stresses for triangular element. If I'll go for a rectangular element, at that time there will be no shear stress, because there is no angle change. If there is no change in angle, or there is no distortion will occur, or if there is perpendicularity will be maintained, then there will be no shear strain. If there is no shear strain, then there will be no shear stress. So based on that, we will see everywhere. It may come to your mind during the discussion, why triangular element. Before the discussing that, or why I have taken as a triangle, as I said, it is the main motto. And the second part, the angle, as I said, here is this theta we are considering from here, or if I am changing this angle, then how only the change of angle, this theta will change. Whatever we have applied over here, these thetas are going to be changed. Otherwise, all the other things will be same. If a tensile load P is applied on the cross section, as it has been said, just now what I have discussed, the same thing has been extended over here for the all different cases. Initially, I have talked about the condition regarding the if it is a beam. Instead of that, now I am coming in a 2D form. 2D form, I am just putting all this whatever we have just now discussed. In the both the time we have discussed the same thing. The first of all, before going to the principal stresses, we talked about the inclined plane and how the stresses have been calculated. Now we started with the principal stress. Principal stress has been classified. Evaluation of the principal stress has been classified into two different phases. One is analytical phase, one is graphical phase. And in analytical phase, we start with the direct stress condition, or sorry, uniaxial stress condition. So these are the stresses we are talking about. Now we can get this the force by the total force on a normal plane B and the sectional area along the plane B. I think it is almost all point we have clarified twice, so I need not to explain more on these slides. So I am directly going to the two-dimensional stresses. We know the total stress component on an element is 18. Again, on the faces, six faces of a cube, if I take, so it is we took as a 18. So all six faces 3, so it is 18. Out of 18, we take again only 9, because all this normal 3 will have a another normal 3. So sigma x of minus sigma x, sigma y and minus sigma y, sigma z and minus sigma z. So we took the positive part. Similarly, a pair of out of the pair of normal stress, we took a half of that, and a group of shear stress. Out of the group of shear stress, we took again minus of that, we have not taken. Out of 6 we sorry, out of 12 we take only 6, because 6 faces, each face will have 2 shear stress, so we will get 12 component of the shear stress, and each faces will have one normal stress. It will have 3 component, and it will have 3 corresponding pairs, so we will take 3 normal and 6 shear, so we will get 9 instead of 18. So all the stress components are equal in magnitude and opposite in direction on the corresponding plane we took in that. Again, using complementary shear stress are equal, we know tau xy is equal to yx. Again, it is being reduced to the form, any form has been reduced. That means out of 9, again it reduced. Normal stress, we know every time, as I said, every time the normal stresses will come in pair. Just see, if it is positive sigma y, if I'll take this one, so it will be the negative sigma y, I am not going to consider. If it is positive sigma x, I am going to take, so I am not going to take the negative sigma x here. So similarly, the sigma z, if I am taking the perpendicular to this, if I am considering positive, then I will not take this one. Or if the towards outward the plane, if I am taking positive, then the second part will not take. Similarly, the shear stress will have, all shear stress will have two components of 6 12 6 2 are 12, so 12 components, out of which we will take 6 components. In a 2D case, the first biaxial and normal shear stress condition, as I said, the last one, if I'll discuss and I'll drop one of them, if I'll drop the shear stress, then I'll get the biaxial normal stress. If I'll drop the biaxial normal stress, then I'll get the final one. Sorry, pure shear condition. Similarly, we'll just take an element of the body, as I said, just cutting of the body, what I have shown there. If I'll take the similar way, let's say the cut, and I took, these are the theta, and from where to in which angle I am considering, or which direction I am considering, it depends upon that. The direction anti-clockwise and clockwise will be decided. So this theta I have taken, and on this inclined plane there are 2 normal and 2 stress components will develop, which is a principal stress component, or you can say the stresses on inclined plane will develop. One is normal component, one is shear component, and the forces, this is the force equilibrium diagram. And the forces, because you just see, we have taken as a unit thickness of this. That means instead of this, if I'll show the structural component or the component like this way, if I'll show, it will have a unit thickness on here. So then it will just, all these areas, we are talking about all these areas. Although we could not able to see the area, but this is like looking like this area will be on that the ds will be working, and this ds into 1, this unit thickness, so sigma theta ds into 1, which will give you the normal stress on this inclined plane. Tau theta ds into 1 will give the shear stress, shear force on this plane. This is a normal force, and this is the shear force. Now the corresponding normal stress and the shear stresses are developed based on this, and you can see some of the book also followed. Instead of the shear stress, you will have a half of the arrow. I think I also told why the half of the arrow during my common classes or online classes. During my live classes, I have discussed why the half of the arrow normally shown. Now, if I'll take the force equilibrium diagram, then I have to take all the forces wherever the summation of fx, because I need to calculate the resultant force. In order to calculate the resultant forces, I have to all these forces, or all these points, whatever it is there, I need to first of all take all these points. That means this normal and the shear components in different plane, I have to normalize that by using free body diagram. Now if I started the free body diagram, this is the one part where the normal and shear components are corresponding to the x and y. I think it is now clear. From this figure it can be clear, clarify your ideas. One is what are the y component, and the corresponding the x component has been shown. So sigma x dy, it is sigma x dy into 1. So the sigma x, if it is the sigma x, because we are trying to compute this sigma x and sigma y, we are trying to compute with respect to this sigma theta. That means whatever the sigma x I am having here, sigma x dy is the force, dy into 1. So sigma x dy into 1 into cos theta will give you, or if I multiply in other way also, sigma y dx or dy into 1 into cos theta, it will equalizes with the sigma theta ds and sigma theta ds1. Similarly, tau y ds theta, all sigma y sigma x dy cos theta, tau y dy sin theta, and the corresponding sigma x dy and tau dy. Please find out this when we are going through the video lecture. You please see all these components should be correct. If it is not correct, please make me correct also. So there might be some typographical error. I think most of the part I have looking into that, based on that I made. So please you look into a little bit more. Um, Typically, I tried my best to do that. So please. So now if I'll just draw all this kind after the finding out the free body diagram for all different planes corresponding to the sigma theta and tau theta. Now I can equate this equation, this considering unit thickness, then I can write the force equilibrium condition. All the forces along the sigma theta ds has to be equal to 0, and all the forces along the shear stress equal to 0. Now the all the forces along the shear normal stress equal to 0 by putting when I am putting that, I can write sigma theta ds and sigma x dy cos theta minus sigma y dx sin theta minus tau dy sin theta minus tau dx cos theta is equal to 0, and based on that I can finally put reach a point sigma theta is equal to just this ds I am dividing from all this. Now what we know from ds earlier, if I'll put in that form, and now the sigma theta, the final, I'll just put here instead of this is dy cos theta, and I'll put here ds, here ds, here ds, and all everywhere if I'll put the ds. So ds is automatically, if I'll remember the first slide, so ds is nothing but, again, ds is nothing but, ds is the hypotenuse of that, and dy is the base, and this is the theta. So p by h or b by h, based on that cos theta and sin theta can be obtained, and the corresponding cos theta and sin theta has been turned to ds to dy by cos theta and dx by sin theta. So dy by cos theta will be multiplied again over, so sigma x dy cos square theta. I think it is now it is clear by dividing this ds and changing this ds by dy by cos theta and dx by sin theta, putting all this into at a time, we can get again the same figure whatever we have followed earlier. Now we can get directly the sigma x is equal to, by utilizing whatever we have discussed in the first discussion. During that time we wrote cos square theta is equal to 1 plus cos theta, or half of 1 plus cos theta, like that we have written. So now it has been converted into this form. The same sigma theta has been converted into trigonometric form, and we get sigma theta is equal to sigma x plus sigma y by 2. You see, we have started with the sigma x, sigma y, and tau on a different plane. Now we convert all this sigma x, sigma y, and tau xy in a single form, or we are trying to represent the multiple kind of stresses in a single normal form of sigma theta. It is nothing but the resultant forces or resultant stress develops on that body, on a particular element, by applying the different or a combination or a group of stresses onto that. And we know whenever we will apply a load, there is a combination of stress will develop. If the combination of the stress will develop, then how to do so? And this is nothing but the principal stress give us to find out the resultant stresses in their corresponding planes. Now similarly, the sigma theta, as we resolved for the normal stress, we can resolve for the shear stress as well, and by taking plane with maximum stress is now finding the derivative. In order to find out, once I'll get the sigma theta and tau theta, now I want to find out the plane with maximum stresses. Why so? Because I know, first of all I need to know the principal plane. In order to find the principal plane, to find out the principal plane, there are I have to utilize some kind of condition, and I wrote first. I started with plane with maximum stress, the plane which contain the maximum stress how much, because we are bothered about the maximum stress only, and is it below the allowable stress or more than allowable stress, it is our lookout. As a design engineer, every time we look out in that way. So the principal stress and the maximum principal stress and the minimum principal stress, or maximum shear stress or minimum shear stress, by which that condition we can able to know. Now the sigma theta, the data we got earlier, if I'll just if I want to know the maximum principal stress, that means the derivative of the condition, the derivative of that particular, the mathematics has given us all this kind of procedure. That means the rate of change of sigma theta, if the first derivative is equal to 0, that will give you the maximum plane. So now derivative by doing the derivative to the sigma theta expression with respect to theta, we can get minus sigma x minus sigma y sine 2 theta plus 2 tau cos 2 tau cos 2 theta is equal to 0. Based on that, we will get the plane. If I am interested to find out the plane is nothing but another place where what is the distance from where the structure is available, or from where, sorry, the plane at which the maximum principal stress exist. It is the plane it was applied, the load was applied earlier, the load was applied like if the load was applied in a horizontal plane and a vertical plane. Now we are finding out the next plane where this is sigma x or sigma theta was there. So now the plane, that sigma theta contains the plane, that is the resultant, and what is the maximum value, which plane, out of which plane where the maximum principal stress exists. To find out that, we derivative the value of sigma theta, and by doing so we can get only an angular form we are going to get, and that angular form tan 2 theta is equal to 2 tau by sigma x minus sigma y. And if I'll just try to draw to find out this value, so I can easily find out. That means a triangle will have, because tan 2 theta is equal to p by b, that means the plane which you will get, that plane will have 2 tau, and but the angle is, I can show you in a next plane here. So now the 2 tau by whatever we got stress on a principal plane, similarly we can get here. I can go, if I'll draw the same thing whatever we have discussed, if I'll draw, then I can get this 2 tau. That means one is 2 tau and p by b, this is the 2 tau, and this is 2 theta, this angle is 2 theta instead of, but we started with the theta only. Now we reached 2 theta. You just remember that part, we will discuss about that later. So here it is 2 tau, and this is p and this is b, accordingly I'll get. Now the plane, if I want to stress on the principal plane, if I want to get, these are the if this is 2 tau, I know this is 2 tau, just now we have drawn, and this is sigma x minus sigma y, and this is the hypotenuse of that triangle. Now the sine 2 theta value I can get, because I got the tan 2 theta. Once from tan 2 theta I got this angle, this is p by h, and next is b by h. By putting this p by h and b by h, now put these values, this sigma theta expression, if I put those values, I can directly get, because I got earlier half of sigma x plus sigma y plus or minus half of sigma x minus sigma y. By putting cos 2 theta and sin 2 theta values, I'll reach a new what is this 1 and 2. You see, this 1 and 2 will give you a positive value and a negative value, because we will have a maximum and minimum. The same tan have two different values, same sine have two different value of different angle. If this is 2 theta, then it is from here some, this is has to be, it is 180 degree altogether, it is 180 degree. So if it is 180 degrees, so one part has been taken, the other part from that side how much. So similarly, one is principal plane and maximum principal stress and minimum principal stresses. By taking this plus or minus value, I can get the final step like this form. That means sigma 1, which is the maximum principal stress, give you the sigma x plus sigma y by 2 plus half of sigma x minus sigma y square plus 4 tau square, and sigma 2 value is the minimum principal stress is this much. I believe this much is clear about the principal stresses which is occurred due to the combination of normal and shear stresses in different perpendicular planes or mutually perpendicular plane. If the mutually perpendicular plane it is occurring, then what to then the what is the resultant stresses is are going to develop on an inclined plane. Then what are the principal stresses are going to develop? Now these are the principal stresses, or these are the due to the application of sigma x, sigma y and tau xy, we are going to get sigma x, sigma y and tau xy. The maximum principal stress generated on a inclined plane is this much, and the minimum principal stress is generating at this much. I believe this is the steps by which mathematically we can calculate the principal stresses and the corresponding principal plane. And this tan 2 theta is equal to 2 tau by sigma x minus sigma y, just now we have discussed. What we understand that at any point within a stressed body, no matter how complex the state of stress, maybe there always exist of three mutually perpendicular planes, and this on each which the resultant normal is resultant force is normal to that. These are known as principal planes, and the stresses across the plane is termed as principal stress. In two-dimensional problem, one principal value or one principal stress value is 0. From the rest two stresses, the higher value is called the maximum principal stress and the lower value is called minimum principal stress. Similarly, the maximum shear stress condition also can be calculated by just doing the similar kind of steps. We follow, if I follow the similar kind of step, I can get the principal plane position as well as the principal plane as well as the corresponding maximum principal and maximum shear stress value as well. By putting these values, I can get the maximum principal stress or the maximum shear stress value. You can get the maximum shear stress value and the minimum shear stress value. The first part of that stress, that means sigma x plus sigma y by 2, will not be there. All the other things, that means the combination of the shear stress, we may find. Inclination of this plane is measured in clockwise. Here the tau theta what we are getting here, the inclination of this plane is measured in clockwise direction. The inclination of the plane means the inclination of the plane we are talking about. The inclination of the plane here, the angular element or the triangular element we took, the inclination of the plane with respect to the inclination of the plane is measured is clockwise. The inclination plane is measured is clockwise with respect to vertical plane VP. This is the angle theta, and the angle we took in a clockwise manner. This is the theta has been taken clockwise, and the compressive stress, that means it is compressive stress or negative, so that's why you will get a -1. So if I take the inclination plane is in this direction, then I may get a positive value. So this is the after finding out the stresses or after the finding out the values of tan 2 theta, it can be plotted in this form. And tan 2 theta we write if where the plane is at a distance of tan 2 theta. And you may as I said, you may ask me why, although there is the triangular element we took, the sigma x and sigma y, we are saying they are mutually perpendicular to each other. If they are mutually perpendicular to each other, then instead of theta, where from this 2 theta come from here. So I'll discuss about that at the last. What are the other conditions? As I just now said, if I am considering the angle, the earlier case, if I am considering the angle theta here, if I'll take the angle here, or if I'll take this angle theta, then what are the consequences or what are the values of the normal and shear stresses? We'll discuss about those in the following lines. For the different cases, inclination of the plane is measured in the counterclockwise. Earlier case we have taken clockwise from vertical plane from this side. If it is counterclockwise, then what are the normal stress? You see, the values are not going to change except this one is a as it is, the normal stress is not going to change if it is direction changes. But here instead of minus, we will have a plus sign, tau theta. And inclination of the plane is measured counterclockwise with respect to horizontal plane. That means if I am taking the angular line, if I am taking the triangular element, and once I'll take either this is theta or 90 minus theta. When I am saying that if it is theta, it is 90 minus theta. That means once I am taking the angle of the plane or angular plane or the place of the plane at a distance of theta from the vertical plane, or 90 minus theta if I am measuring the angle from the vertical plane or horizontal plane, accordingly the expressions are going to change. all the other things will be same based on just put these theta values are a different way. So inclination of the plane is measured from clockwise direction, then how to represent the sigma theta, tau theta, just to have all different kind of cases. If you just see only the plus or minus values are going to change, all the other things will be same. It is not going to change much. So before going to the principal strains, I'll little bit talk about this one. That means if I'm having this normal stress, as I said, if I have started with the plane, I have started with the plane which is theta, but I reached at 2 theta. Where from? I'll give an example like this. That means initially when we have started, you see, initially when we have started that in this form, like let's say the triangular element, and the triangular element is the theta has been taken, and sigma x in this direction, and sigma y is in this direction. They are mutually perpendicular to each other. That means initially when I have taken it's a sigma x and sigma y, sigma x and sigma y at this direction, and vertical plane I got the sigma x, and the horizontal plane I got the sigma y. Now I am calculating this sigma x and sigma y on a single plane, which is, now I have started with theta, I reached at 2 theta. That means now the sigma x and sigma y are the combination, sigma x, sigma y and tau xi are the combination, and that combination has been, now I am making it flat. Instead of in 90-degree, I am making it flat. All the sigma, that means the plane which contains sigma x in vertical plane, and tau x or tau value in a vertical plane. Similarly, the horizontal plane keeps the sigma y and the tau. Now I am opening the sigma x, sigma y, everything on a single plane. If it is on a single plane, then sigma x and sigma y, which we are mutually perpendicular to each other at a 90-degree. Now, if I am opening it, then they have been shifted to a 180-degree difference. So, the angle started with the 2 theta, the angle which is started with the theta, or this is 90 minus theta, now it is converted to 2 theta. That means the mutually perpendicular planes now has been separated. Instead of theta is 2 theta, because instead of 90 they are at a distance of 180-degree. So this is the main concept behind it, or based on that it has been calculated. And if many more any more questions will be there, we can discuss. But beforehand, I'll just talk about little bit on principal stresses, principal strain. What is again principal strain? The same thing. If I know the stress, so I can able to calculate the strain easily. I can able to calculate the strain. If I am easily calculate the strain, what exactly happen in the strain, that's what it is written here. It says the principal strains will be calculated using the similar steps as in the identical to the for computing principal stresses. The only potential pitfall to keep in mind, that means earlier we are taking tau, instead of tau we will write gamma by 2, because I think we have also discussed earlier during the discussion of the shear stress or shear strain, we have discussed. That means instead of a rectangle, if I am talking about a rectangle, initially I have started the cross section, because shear strain talks about the perpendicularity mismatch. If the perpendicularity mismatch, and during the discussion of the shear strain also we have already discussed about those points during the calculation of the epsilon x, epsilon y. One of my lecture I have discussed, already I have discussed. You remember, this is alpha and beta we are talking about. Now here the shear strain, when I am talking about, I am talking about only one plane of that, or one sided angle of that, and that is instead of tau we will take tau gamma by 2, because this is a principal strain, and that means instead of sigma x I will take epsilon x, instead of sigma y I will take epsilon y, and instead of tau I will take gamma xy, and or gamma xy or gamma, or instead of gamma xy I will take gamma xy by 2. So the it will also follow the similar kind of things, that means similar kind of expression. Epsilon sigma x x cos square theta, sigma y y sin square theta, similar form. Instead of 2 tau, you see we have, instead of 2 tau we have 2 gamma xy by 2. So everything will be same, except this part is going to change. Everything will be same except this part is going to change. That means tau will be replaced by the gamma xy by 2. This is the all about principal stress and principal strain and analytical method to discuss about the. And here I have given the link where you can say this principal plane concept without any mathematics also you can see the it is nicely mentioned. And some of the question I have given here for your homework, you please go through these questions and try to find out, try to solve. And if it is not possible, then please ready to ask me something whatever you have in your mind. You can comment in your comment box, you can comment it, or you can write me mail directly. I'll ready to explain all this different kind. And thank you.